By the late 1930s, military planners across the world had reached a similar conclusion about the future of warfare. Geography was no longer protection. Advances in aviation had reduced oceans and continents to distances that could be crossed within hours instead of days. The idea that fleets or borders alone could protect a nation was becoming outdated. Air power was quickly emerging as the decisive factor in modern conflict. During the First World War, aircraft had been fragile machines, useful mostly for reconnaissance or short-range bombing. But in the decades that followed, rapid technological improvements changed everything. Engines became more powerful and more reliable. Airframes grew stronger. Navigation techniques improved. Radios allowed coordination across long distances. For the first time in history, it became realistic to imagine aircraft flying hundreds or even thousands of kilometers to strike deep behind enemy lines. Major powers began investing heavily in long-range bombers. The theory was simple. If an aircraft could reach factories, ports, or cities far from the battlefield, it could weaken an enemy's industry without direct confrontation. Strategic bombing promised results that armies alone could not achieve. Japan faced a particularly complex version of this problem. Unlike continental nations, Japan depended almost entirely on maritime routes. Its empire stretched across islands separated by vast areas of open ocean. Defending this territory required aircraft that could patrol enormous distances. At the same time, any offensive strategy would require bombers capable of reaching targets far beyond conventional range. Existing Japanese bombers were not designed for this role. Most were twin-engined aircraft optimized for regional operations. They were effective for tactical missions, but their endurance was limited. Even with maximum fuel, their operational radius was insufficient for true strategic strikes. If Japan wanted to project power across the Pacific, something much larger would be necessary. Naval planners studied foreign developments carefully. Intelligence reports from Europe described four-engined heavy bombers under development in Germany and Britain. These aircraft promised greater payload capacity and longer range than anything currently in Japanese service. But what concerned them most were developments in the United States. American manufacturers were experimenting with very large civilian transports. These aircraft were not designed for war, but their size and range suggested military potential. A large airliner could easily be adapted into a bomber or transport platform. In fact, many military aircraft historically began as civilian designs. This possibility created urgency inside the Imperial Japanese Navy. If the United States successfully developed long-range four-engined aircraft first, Japan could quickly lose strategic balance. American bombers could threaten Japanese bases and shipping lanes from distances previously considered safe. The ocean would no longer serve as a barrier. To prevent this, the Navy issued new requirements to domestic manufacturers. They wanted a true heavy aircraft. 4 engines, long endurance, large payload capacity, suitable for patrol, transport, or bombing missions. It needed to operate far from base and remain airborne for many hours. On paper, the requirements sounded reasonable. In reality, it demanded an entirely new level of industrial capability. Japanese aviation companies had extensive experience with fighters, dive bombers, and torpedo aircraft. But building a large 4-engine machine required different engineering knowledge. Complex landing gear systems, high-capacity fuel management, reinforced wings, and structural designs capable of supporting far greater weight. These were not simply larger versions of existing planes. They were fundamentally different machines. Designing one from scratch would take years of research and testing, and Japan did not believe it had years to spare. The international situation was deteriorating quickly. Tensions in China were escalating. Relations with Western powers were worsening. Military leaders expected conflict sooner than later. time became the most valuable resource. So when reports emerged of an unusual American aircraft, a massive prototype airliner that airlines considered too expensive and impractical, Japanese planners saw something they had not expected: an opportunity. Instead of spending years developing a heavy aircraft from nothing, they might acquire an existing design and study it directly. To them, it looked like a shortcut to parity. Buy the aircraft, disassemble it, copy it, improve it. Simple in theory, dangerous in practice. But at the time, it seemed like the fastest solution available, and that decision would shape everything that followed. While Japan debated how to build a heavy aircraft, the United States was experiencing a different kind of aviation revolution. The American airline industry was expanding rapidly throughout the 1930s. Passenger demand increased every year. Routes grew longer. Companies competed to offer faster, safer, and more comfortable service. This competition pushed manufacturers toward larger and more sophisticated designs. Douglas Aircraft Company, already known for successful transports like the DC-3, decided to pursue something far more ambitious. Engineers envisioned a next-generation airliner that could carry significantly more passengers while introducing advanced safety features and modern systems that had never been attempted on civilian aircraft. The result was the DC-4E. At the time of its design, it was one of the most advanced commercial aircraft in the world. It used 4 powerful radial engines instead of 2, providing greater redundancy and improved reliability over long distances. The fuselage was spacious and structurally reinforced. Electrical systems were modernized. Instrumentation was more comprehensive than anything airlines had previously operated. Most notably, it introduced tricycle landing gear. Instead of the traditional tail-dragger configuration, the aircraft sat level on the ground, improving visibility for pilots and simplifying takeoff and landing. Today, this design is standard. In the 1930s, it was revolutionary. From an engineering perspective, the aircraft represented the future of air travel. Test pilots praised its stability and handling. Designers considered it a technological milestone. But airlines evaluated it differently. They cared less about innovation and more about operating costs, and the DC-4E was expensive. It required more maintenance hours than smaller aircraft. Spare parts were complex. Fuel consumption was higher than expected. Ground crews needed additional training. Turnaround times increased. All these factors reduced profitability. In commercial aviation, even small cost increases matter. For most airlines, the math simply did not work. Despite its advanced design, the aircraft was judged impractical. Orders were canceled. Only one prototype remained. For Douglas, it became a valuable research platform, but not a commercial success. For Japanese observers, however, the situation looked very different. They did not see a failed airliner. They saw a fully developed 4-engine aircraft, exactly the kind they needed, already built, already tested, and available for purchase. To them, this was not a rejection, it was an opportunity. Through indirect civilian channels, negotiations quietly began. Officially, the purchase was for evaluation and transport research. Unofficially, the aircraft would be studied, copied, and adapted for military use. In 1939, the prototype was shipped across the Pacific. Crated, disassembled, and loaded onto a transport vessel, it traveled thousands of kilometers away from the country that created it. Few people at the time realized what was happening. An aircraft that represented the cutting edge of American engineering was being handed piece by piece to a potential future enemy. Japan believed it had just acquired years of technological progress overnight. What they didn't yet understand was that engineering knowledge cannot simply be bought, it has to be learned. And that lesson would soon become painfully clear. When the American aircraft finally arrived in Japan, it did not resemble a complete machine. It arrived in pieces. Large wooden crates containing wings, engine mounts, landing gear assemblies, control surfaces, wiring bundles, and fuselage sections were unloaded carefully at the docks before being transported inland by rail. To an outside observer, it might have looked like spare parts, but to the engineers waiting at Nakajima's facilities, it represented something far more important. It was supposed to be a shortcut. The plan appeared logical. Instead of spending years designing a heavy four-engine aircraft from scratch, they would simply study the American prototype, measure every component, reproduce the parts domestically, and then adapt the design to meet military requirements. In theory, this approach would save both time and money. Reverse engineering had worked before in simpler technologies. But an aircraft of this scale was not simple. The moment disassembly began, problems appeared. The first issue was documentation. The aircraft had not arrived with complete technical manuals or manufacturing notes. Many of the design decisions made by Douglas engineers were never written down because they were considered routine knowledge inside the company. Tolerances, stress calculations, and material treatments were often based on internal standards developed over years of experience. Without those notes, Japanese engineers were forced to guess. The second issue involved materials. American aluminum alloys differed from those commonly available in Japan. Some structural members used compositions that local factories could not reproduce exactly. Substitutions had to be made, and even small changes in material strength affected weight and durability. Every substitution required reinforcement. Every reinforcement increased mass, and increased mass meant reduced performance. Then there were the manufacturing techniques. Douglas factories relied on specialized tooling and precision equipment that did not exist in the same form in Japan. Rivet patterns, machining tolerances, and assembly methods were optimized for American production lines. Replicating those processes with different tools inevitably introduced inconsistencies. Small misalignments accumulated across the structure. Nothing was dramatically wrong, but nothing was perfectly right either. The landing gear proved especially difficult. The tricycle configuration was still relatively new, and its hydraulic mechanisms were complex. Engineers struggled to reproduce the exact geometry and reliability of the original. Tests suggested that the system might not tolerate the higher weight expected in a military conversion. Fuel systems presented another challenge. Long-range aircraft required intricate plumbing to balance fuel loads between tanks. Without complete schematics, recreating these systems became trial and error. Improper balancing could destabilize the aircraft during flight. Even cockpit instrumentation caused confusion. Units of measurement differed. Some gauges used American standards unfamiliar to local crews. Conversions introduced further inaccuracies. As weeks turned into months, the realization grew unavoidable. They could copy the shape of the aircraft, but they could not copy the knowledge behind it. An airplane is not just metal and engines. It is thousands of small engineering decisions refined through testing and experience. Without that invisible background, replication becomes approximation. And approximation in aviation is dangerous. Still, the Navy's expectations did not change. Money had already been invested. Senior officers had publicly supported the project. Admitting failure before the first prototype even flew was politically unacceptable. So instead of questioning the approach, pressure increased. Engineers were instructed to continue, modify what they could, simplify what they didn't understand, make it fly. Eventually, the modified design received a new designation, G5N. It was no longer an American airliner. It was now intended to be Japan's first true heavy bomber. But by the time the first airframe neared completion, it already carried the hidden weight of countless compromises, and none of them would remain hidden for long. By early completion, the new aircraft looked impressive at a distance. It was undeniably large, far bigger than most bombers currently in Japanese service. With 4 engines mounted across a wide wingspan and a long, reinforced fuselage, it visually matched the image of a heavy strategic aircraft. On paper, it appeared to meet many of the Navy's original requirements. But engineers knew that paper specifications meant little without real performance. Ground testing began cautiously. Even before flight, warning signs emerged. During taxi trials, the aircraft required unusually high engine power just to begin moving. Mechanics noticed that the airframe felt heavier than predicted. Reinforcements added during construction had gradually increased total weight far beyond initial estimates. This excess mass affected everything. Brakes overheated easily. Steering felt sluggish. The landing gear strained under load. Small cracks began appearing near mounting points after repeated movement across uneven surfaces. If the aircraft was already stressed on the ground, what would happen in the air? Engine run-ups produced additional concerns. Cooling airflow was less efficient than on the original American design. Modified engine mounts altered airflow patterns, causing higher operating temperatures. Crews had to monitor instruments constantly to prevent overheating. Still, cancellation was not considered. Orders were given to proceed with the first flight. Test pilots approached the mission with caution rather than excitement. Large multi-engine aircraft carried higher risk. If multiple engines failed or performance proved insufficient, recovery options were limited. The takeoff roll confirmed their fears. Acceleration was slow. Observers along the runway watched the bomber consume nearly the entire strip before lifting off. Instead of climbing decisively, it rose gradually, barely clearing obstacles at the end of the field. Inside the cockpit, control forces felt heavy. Banking required strong input. The aircraft responded slowly to corrections. It felt less like a modern bomber and more like an overloaded transport struggling to stay airborne. Performance measurements were disappointing. Top speed fell short of targets. Climb rate was poor. Range estimates dropped once actual fuel consumption was recorded. Bomb load capacity had to be reduced simply to maintain safe flight margins. In practical terms, it could not fulfill its intended mission. Reliability proved even worse. Hydraulic leaks appeared only after a few sorties. Electrical systems malfunctioned. Engines required frequent maintenance. Each flight was followed by days of repair work. Instead of preparing for combat deployment, the aircraft spent most of its time inside hangars. Engineers recommended further redesigns. Each redesign meant more delays. Each delay increased costs. Meanwhile, the international situation was deteriorating rapidly. War was no longer theoretical. Combat demands were immediate. The Navy began asking uncomfortable questions. Was this aircraft worth the resources? Could those resources produce more useful machines elsewhere? For the first time, the assumption that copying a foreign design would save time started to look dangerously optimistic. What was meant to be a shortcut was turning into a detour, and the bill was still growing. By the time multiple prototypes of the new aircraft were available for evaluation, the strategic situation in the Pacific had changed dramatically. What had once been a long-term modernization effort was now competing with immediate wartime demands. Political tensions had escalated into open conflict. Factories were under pressure to deliver usable aircraft as quickly as possible. Commanders at the front were not asking for experimental machines. They were asking for reliability. And reliability was precisely what the heavy bomber could not provide. Every flight test revealed the same pattern. The aircraft required extensive maintenance before and after each sortie. Engine inspections took longer than expected. Spare parts were scarce. Small mechanical failures forced cancellations. What should have been a straightforward training flight could turn into an entire day of troubleshooting. For frontline operations, this was unacceptable. A bomber that spends most of its time on the ground is not a bomber. It is simply a liability. Logistics officers began calculating the true cost of keeping the program alive. The numbers were difficult to justify. The aluminum required for one heavy aircraft could produce several medium bombers or dozens of fighters.
Engine production capacity was limited, and each four-engine machine consumed power plants that might otherwise equip multiple smaller aircraft. In a total war economy, efficiency matters more than ambition. There was also the issue of infrastructure. Large bombers required longer and stronger runways. Many forward bases across the Pacific were small, improvised airstrips carved out of jungle or coral. They were adequate for fighters and medium aircraft, but unsuitable for a machine of this size and weight. This meant the heavy bomber could only operate from a small number of major bases. That reduced flexibility, and reduced flexibility meant reduced usefulness. Training crews added another complication. Pilots accustomed to lighter aircraft needed additional instruction to handle the bomber's weight and systems. Mechanics required specialized knowledge. Ground equipment had to be upgraded. All of this consumed time that commanders felt they did not have. Meanwhile, real combat data was challenging the entire concept of heavy bombers in the region. Twin-engined aircraft operating in coordinated formations were achieving many of the same objectives with fewer resources. They were faster to build, easier to maintain, and more adaptable to rough airfields. In practice, several smaller aircraft often accomplished more than one large one. Reports from operational units were blunt. The heavy bomber did not offer enough advantages to justify its complexity. Comparisons with foreign developments were equally discouraging. American four-engine bombers were demonstrating superior speed, payload, and durability. More importantly, the United States possessed the industrial capacity to refine those designs quickly. Problems identified in 1 month could be corrected in the next production batch. Japan lacked that luxury. Every modification required lengthy delays and careful allocation of scarce materials. As weeks passed, internal meetings became less optimistic. Early discussions about performance improvements were replaced with more pragmatic questions. Could the aircraft be simplified? Could it be converted into something else? Could any value at all be salvaged? Eventually, a quiet consensus formed. The bomber program, as originally envisioned, had failed. Not because the idea of a heavy aircraft was wrong, but because the industrial and technical foundation required to support it simply did not exist. Continuing development would only consume more money and time without changing the outcome, and wartime leadership had neither to spare. One by one, expectations were lowered. Bombing missions were removed from planning documents. The aircraft's role was reconsidered. Instead of a strategic weapon, it would become something far less ambitious, a transport, a machine designed to carry cargo rather than explosives. For an aircraft that had once promised to reshape naval aviation, it was a quiet and almost humiliating reassignment. But at least it offered a way to recover something from the investment, even if that something was far smaller than originally promised.
In the end, only a small number of aircraft were completed. Far fewer than originally projected. None of them ever served as operational heavy bombers. Instead, they were converted for transport duties, moving personnel, equipment, and supplies between rear area bases. Their large internal volume made them moderately useful for this purpose, but even here, their limitations remained obvious. Maintenance crews often described them as temperamental. Engines required constant attention, spare parts were difficult to source, availability rates were low. When compared to purpose-built transports, the aircraft offered no significant advantage. For a program that had consumed years of development and substantial funding, the operational impact was minimal. Most missions were routine logistics flights. No major battles were influenced, no decisive strikes were carried out. The aircraft simply existed, performing minor tasks while newer and more efficient designs took priority. Eventually, some airframes were grounded permanently due to mechanical wear, others were dismantled for parts. Few photographs survived. Official documentation remained limited. As the war intensified, attention shifted to more urgent matters. The project faded quietly into obscurity. But from an engineering perspective, it left behind important lessons. The first lesson concerned reverse engineering. Purchasing or copying hardware does not automatically transfer the knowledge required to build it successfully. behind every aircraft is an entire ecosystem of expertise, material science, testing procedures, manufacturing precision, and years of accumulated experience. Without that foundation, even an exact copy can perform worse than the original. The second lesson involved large industrial scale. Large aircraft demand large infrastructure. Without factories capable of consistent, high-precision production, reliability suffers, and without reliability, military usefulness disappears. The third lesson was organizational. Once large sums of money and prestige become attached to a project, it becomes politically difficult to cancel it. Programs continue longer than logic suggests. Resources are consumed not because success is likely, but because admitting failure feels unacceptable. In wartime, that hesitation carries a cost. Looking back, historians often describe the aircraft as an example of misplaced optimism. Leaders believed technology could be acquired quickly and cheaply simply by obtaining the physical machine. Reality proved more complicated. Experience cannot be crated and shipped. It has to be built slowly. Ironically, the American company that created the original prototype did learn from its mistakes. Douglas used the knowledge gained during development to design improved transports that became reliable wartime workhorses. In the United States, the project evolved into success. In Japan, it became a footnote. Today, the aircraft is rarely mentioned in broader histories of the war. It did not participate in famous battles or dramatic events, yet its story remains valuable precisely because it was not successful. It reminds us that military history is not only shaped by victories and breakthroughs, it is also shaped by failures, miscalculations, and expensive experiments that never deliver what they promise. Sometimes the most revealing stories are not about the machines that changed the war, but about the ones that never truly left the ground. If you found this forgotten aviation story interesting, consider subscribing for more detailed documentaries about overlooked aircraft and secret wartime projects. And tell us in the comments which hidden chapter of history you'd like to explore next. Because not every weapon becomes legendary. Some simply become lessons.